This is Chapter 8, Gases. The final section, 8.8, is partial pressure and Dalton's law. To understand partial pressure and what it means, it helps to first imagine a container with a fixed volume and temperature that has two different types of gases in it. So in this case, we have this container over on the right-hand side, and it has some orange gas particles and some purple gas particles. What they actually are doesn't really matter. We just want to be able to tell them apart. Okay? So in total, this container has n total gas particles. That's the total number of moles of gas particles. According to the kinetic theory of gases, since the individual particles don't interact with one another or affect anything through their mass or their identity, the pressure really only depends on the total number of particles. Okay? So the total pressure of this mixture of gases in this container equals nRT divided by V, where the n is the total number of moles, n total. Now we can imagine the same container at the same temperature. It'll have the same volume because it's the same container, but we've taken out the purple gas and we've only left the orange gas particles. So what's left behind is the number of moles of orange gas particles, which we're going to call NO. Okay? So the new pressure of this sort of hypothetical situation is just going to be coming from the orange gas particles. So we can say that the pressure of the orange particles is equal to nRT over V, where this time n is NO, the number of orange particles. Okay, so this is clearly going to be less than the total pressure because the number of orange particles was less than the total number of particles. Or we can look at it the other way, right? Imagine that the orange particles are taken away and the purple particles are left, but still it's the same container, so it has the same volume, and we're going to keep it at the same temperature. So now the pressure of these purple particles is going to be the same basic expression. The pressure is equal to nRT divided by V, but now n is the number of purple particles, which we're going to call NP. Okay? So now we can look back at the original mixture and try and figure out what's going on as far as the total pressure. So the total pressure depends on the total number of particles. But the total number of particles really equals the number of orange particles plus the number of purple particles. So we can put this expression in for the total number of particles into the total pressure expression. And so we put it right here, and we get NO plus NP times RT divided by V. Remember, the volume is the same for all the particles because it's just the volume of the container, and the temperature is the same for all of them because you can't really put all of the energy into one type of particle and not the other. So the particles are constantly interacting and sharing energy, and so they're going to come to thermal equilibrium at the same temperature. Okay? So we can put this expression in, and then we can distribute, right? The RT gets distributed by both terms in this sum, NO plus NP. So we get NORT plus NPRT divided by V, and then we can split that up into two separate factors, two separate terms like this, and then we recognize that this is just the expression that we saw in the previous slides for the partial pressure of the orange particles, and this is the expression we saw for the partial pressure of the purple particles. So it turns out that the total pressure of the gas mixture is equal to the partial pressure of one particle type plus the partial pressure of the other particle type. So this is really just Dalton's law of partial pressures. It states that the total pressure exerted by gases in a mixture is just the sum of the partial pressures of those gases. And we just have to remember that the partial pressure is calculated for the individual type of gas as if all of the other gases were not there. Okay, and so we get that the total pressure equals the partial pressure of component 1 plus the partial pressure of component 2 plus the partial pressure of component 3, et cetera, as many different gases as we have in the mixture. Okay? If there's only 2, then you stop at P2. If there's 3, you stop at P3, and so on. So this is a similar illustration, right? We have one tank here with enough helium particles to make a pressure of 2 atmospheres. We have another identical tank, same volume, same temperature, but this has enough argon particles to make a pressure of 4 atmospheres. If we put both of those helium and argon samples together into the same tank, right, one volume, so it has the same volume and the same temperature as the other individual tanks, but now it has enough helium to make 2 atmospheres and enough argon to make 4 atmospheres. So altogether, the total gas particles in the tank is going to make 6 atmospheres of pressure. To take another example, if we have 1 mole of a pure gas at 273 K in a volume of 22.4 liters, then we know that that gas is going to exert a pressure of 1 atmosphere, okay? Because 22.4 liters is the molar volume at standard temperature and pressure. And this is the standard temperature, and so this will be the standard pressure, okay? So this is going to be true for any pure gas that we can find. But if we take instead a mole of a gas mixture at the same temperature and the same volume, okay, then it's still going to exert the same pressure. Okay? So whether we have 1 mole of nitrogen by itself or 1 mole of a mixture that's 40% oxygen and 60% helium, or 1 mole of a mixture that's 3 different gases, 50% oxygen, 30% helium, 20% argon, they're all going to exert the same pressure. As long as the total number of gas particles is 1 mole, then under these conditions, they're always going to exert the same pressure. It doesn't matter how it's split up. And the reason for that is the identity of the particles doesn't affect the properties. So for instance, the air we breathe is a mixture of different gases. It's mostly nitrogen. It's about 78.2% nitrogen and 21% oxygen, and then less than 1% of other trace gases like CO2 and water vapor that we exhale, argon, other things like that. So what we call atmospheric pressure, which is 760 millimeters of mercury, or 1 atmosphere, is really the sum of the partial pressures of those different gas components. So the nitrogen, if the nitrogen in your room were all by itself, it would exert a partial pressure of 594 millimeters of mercury. If the oxygen in your room were all by itself and all the other gases were removed, it would exert a pressure of 160 millimeters of mercury. And then the other trace gases would only exert a pressure of 6 millimeters of mercury if they were by themselves. But so you can add these 3 numbers up and you're going to get the total, which is 760. Just like if you add up these percentages, you're going to get a total of 100%. Okay? And actually, if you look at these percentages, the molar percents will be the same as the partial pressure percentages. So in other words, if we take the total pressure of 760 and we multiply it by 78.2%, 78.2 divided by 100, we're going to get the partial pressure of nitrogen, 594 millimeters of mercury. Okay? If we do the same thing for oxygen, the percentage of oxygen is 21%, so 21 out of 100. This is going to give us 160 millimeters of mercury. Okay? So the mole fraction, or the mole percent, will be in the same proportion as the partial pressures. Partial pressure questions are typically a lot easier than the preceding discussion would probably have you believe. Okay, so there's a lot of mathematics in that and the derivation of partial pressure and all that. If you can understand it and it helps you to remember how the law works, then that's great. If you can't really understand it, then really memorizing the formula is good enough for partial pressures. Okay, the total pressure equals the sum of the individual pressures. That's sufficient to answer most questions dealing with partial pressure in this class. So for this example, a scuba tank contains oxygen, O2, with a pressure of 0.450 atmospheres and helium at 855 millimeters of mercury. Okay. What is the total pressure in millimeters of mercury in the tank, assuming volume and temperature are constant? Okay. So this is clearly a partial pressure problem. They're asking us for the total pressure after giving us individual pressures for the 2 gas components here. So when we analyze the problem, we're going to write down the 2 individual partial pressures. Okay, so this is the partial pressure of oxygen. This is the partial pressure of helium. And it wants the total pressure. Okay. So we're going to try and find the total pressure using Dalton's law. The one trick to this is that you can't add different variables with different units. Okay? If you're adding 2 variables together, they have to have the same unit. You can't add apples to oranges, you have to add apples to apples. So If the question is asking for our answer in millimeters of mercury, then it's going to be most useful to convert the atmospheric pressure to millimeters of mercury. So first step, or the next step I should say, is to convert all pressures to the same unit. So 1 atmosphere equals 760 millimeters of mercury. That means 0.450 atmospheres multiplied by 760 millimeters of mercury per 1 atmosphere will give you an answer of 342 millimeters of mercury. Okay, the atmosphere unit's going to cancel out and we'll be left with millimeters of mercury. So this is going to be our partial pressure of oxygen in the correct unit. Once you have that, it's very easy to solve Dalton's law. You're just adding two things together. So you take the partial pressure of oxygen that you just calculated, the partial pressure of helium, which comes directly from the problem, okay, and you add them together. 342 millimeters of mercury plus 855 millimeters of mercury gives you 1,197 millimeters of mercury. Since both of these measurements are accurate to the ones place, then your answer should be accurate to the ones place. There's no need to round this off or do anything like that. So you actually sort of gain a digit here when you add these two terms together. Another scuba diving example. For a deep dive, a scuba diver uses a mixture of helium and oxygen with a pressure of 8 atmospheres. If the oxygen has a partial pressure of 1,280 millimeters of mercury, what is the partial pressure of the helium? Okay. So in this case, the only confusing thing might be to recognize that this pressure of 8 atmospheres really is talking about the total pressure of the mixture. Okay. It's not just the pressure of the oxygen or helium alone, it's the total pressure of the mixture. So when we analyze the problem, this time we're given one partial pressure for the oxygen and the total pressure. Okay? And we're asked to find the other partial pressure. So we're going to need to take Dalton's law and just do a little bit of rearranging to get the answer. First, though, we have to again make sure all our pressures are in the same unit. The problem statement itself doesn't ask for a specific unit, but this was multiple choice and all of the answers were given in millimeters of mercury. So we're going to convert 8 atmospheres to millimeters of mercury with this conversion factor so that ATM cancels and you're left with 6,080 millimeters of mercury. And then your last step is just substituting these partial pressures into the equation. Like I said, we'll need to rearrange Dalton's law a little bit, so we have to subtract the partial pressure of oxygen from both sides, so we get the partial pressure of helium equals the total pressure minus the partial pressure of oxygen. Okay, it's very simple algebra. And so the total pressure is 6,080 millimeters of mercury, oxygen is 1,280 millimeters of mercury, and so we end up with a partial pressure for helium of 4,800 millimeters of mercury. Okay. Now in this case, this is an insignificant zero and this is an insignificant zero, so when you subtract the two, you're not going to have one's value. So this is really only good to 3 significant figures, which is hard to indicate when it's expressed like this, so you might see this also expressed as 4.80 times 10 to the 3rd millimeters of mercury. Okay? And this will express it with the correct number of significant figures and the coefficient. So this idea of partial pressure can actually help explain how blood transports different gases through your body. So the amount of a gas dissolved in your blood really depends on the pressure of the gas outside, okay? Especially when it's exposed to the atmosphere as it is in your lungs. So when blood starts to flow and it gets to the lungs, the partial pressure of oxygen in the lungs is higher than the dissolved pressure of oxygen in the blood flowing in. And so oxygen diffuses from your lungs into the blood. Okay? The partial pressure of CO2 in your lungs is going to be a lot lower than it is in your blood, and so CO2 is going to diffuse out of the blood and into your lungs to be exhaled. Okay? As a result, so oxygen enters the blood in the lungs and CO2 leaves to be exhaled. Okay? Then the blood gets pumped back, goes back through the heart and onto the tissues. In the tissues, they're constantly using up oxygen for the metabolic processes, so the partial pressure of oxygen in tissues is going to be lower than the pressure of the oxygen dissolved in the blood. And so oxygen is going to go from the blood into the tissues, and vice versa for CO2. Here, the cells are using up oxygen, but they're generating CO2 in their processes. So the CO2 pressure is going to be higher in the tissues, and so CO2 is going to transfer or diffuse from the tissue into the blood. And so this is going to deoxygenate the blood, and that's going to then travel back towards the heart, where it'll be pumped back to the lungs to start the whole process over again. Okay, so this whole thing depends not on the total pressures necessarily changing, but on the individual partial pressures of the different components changing and being different. Okay, so it helps to explain these sort of blood transport processes. Here's a concept map for the entire chapter 8 that shows you all of the different gas laws and gas properties that we need to know, especially for the exam. So some of the more important ones that you want to take a look at are clearly the ideal gas law, although you should know the individual gas laws as well. But the ideal gas law can answer a wide variety of questions. Molar volume is useful. You can use ideal gas law in place of molar volume. Just plug in the standard temperature and pressure properties into PV equals nRT. But it's a useful shortcut if you can remember it. And we also want to know about reactions of gases. Okay, so it's going to be very important for you to know how to convert between the pressure, temperature, and volume to the number of moles so that you can use the moles in a chemical equation. Okay, and then you'll also have some examples on partial pressures. So these are really the most important parts of this chapter.